Now, working with rational functions and their graphs, we do want to be able to identify properties of the functions, much like we've done before now, where we've talked about the asymptotes, both the vertical and the horizontal asymptotes, and the transformations. We're going to add to that our points of discontinuity. And we're going to learn that our points of discontinuity are going to be values that we have where our in our denominator, when our denominator is equal to 0. When our denominator is equal to 0, we are going to have undefined information, and that's why we are going to have points of discontinuity, because they cannot exist. So looking at this first example, what are the points of discontinuity in the domain of this rational function? Well, if I look, I do know that looking at the denominator, I have x squared minus 16, and if I make that equal to 0, I can find a point of discontinuity. And of course, just do some simple inverse operations, and that gives me x squared is going to be equal to 16, and then we find the square root of both sides, and x is going to be equal to plus or minus 4. So if x is plus or minus 4, then we are going to be sitting on a point of discontinuity, because my denominator would be equal to 0. And if you need to check that, you can simply plug in 4 right there, either plus or minus, and you'd find out that 4 squared minus 16 is going to be 16 minus 16, or 0. And that is verifying that point of discontinuity. Call that the point of discontinuity. And then it says, what is the domain of this rational function? Well, remember that the domain is representative of all the values of x, that all the values of x-axis, that this function is considered true. And this function is true at all values of x except for our points of discontinuity. So our domain is going to be equal to all values of x where x is from negative infinity to negative 4, and then from negative 4 to 4, and then we have a break there at 4 for discontinuity, and then it's going to continue on from 4 to positive infinity. So there you go, the domain. Or we could just say, how about all real numbers except plus or minus 4. That's your domain. A little bit long there, but let's see here, this next equation. Is there anything, if we want to make our denominator equal to 0 to find this point of discontinuity, and that would give us x squared plus 3 equals 0. If we subtract 3, do our inverse operations, and I have x squared is equal to negative 3. Have to ask yourself, is there any value that I can square and get a negative number? And hopefully your answer to that is no. Anytime you square something, you're going to have a positive number. So there are no points of discontinuity here, because nothing that you square is going to give you a negative 3. And my domain then, the domain then is going to be from negative infinity to positive infinity, or all real numbers. That's the domain of that function, since there are no points of discontinuity. And let's see here, this last one. I hope you recognize, what I want you to recognize is that this is going to be a factorable quadratic. So this is going to equal to x plus 1 over x plus 1 times x plus 2 is going to be how that factors. And so now we know that, well, x plus 1 over x plus 1 is going to cancel out. And this problem can be rewritten as y equals 1 over x plus 2. And now we should be able to see a, my domain. is going to be all real numbers, but let's think about if I make this denominator right here equal to 0, then I know x plus 1 is equal to 0 and x plus 2 is equal to 0, or x is equal to negative 1, x is equal to negative 2. So my domain is going to be, how about all real numbers except when x equals negative 1 or x and equals negative 2. Not valid domain. And then my points of discontinuity, well, are going to be x equals negative 1, x equals negative 2. And I know that you may say to yourself, well, in this denominator we no longer have that x plus 1, but it still exists. We just made it into 1, therefore it is a point of discontinuity. It's called just a hole that we were able to cover up. Let's see here, vertical asymptotes. That is, again, looking at that point of discontinuity is when your denominator is going to be equal to 0. So what are my vertical asymptotes? Well, I just turn around and make my denominator equal to 0 to find it. And then, of course, this is the zero product property. And you do the zero product property by making both things equal to 0, do your inverse operations. And then we know that x is going to be equal to 1. That is one of my vertical asymptotes. And then x is going to be equal to negative 3. So these both are my vertical asymptotes. Okay, so x is 1, x is negative 3, vertical asymptotes. Now look at this next problem, and we know that x minus 2 over x minus 2 is going to simplify to simply a 1. So my new problem is going to be y equals 1 over x plus 3. And when my denominator is equal to 0, so I have x plus 3 is equal to 0, and of course x is going to be equal to negative 3. That is going to be my vertical asymptote. And let's see, do we need to know anything else? Well, x minus 3 is going to be my vertical asymptote. How about that? That's all you need to know here for this problem. And let's see here. Look at this quadratic in part C. This x squared minus 1, you should recognize that as the difference of squares. So we have x plus 1 times x minus 1 over x plus 1. And I'm looking for a point of discontinuity, or vertical asymptotes, I'm sorry. And I can turn around and simplify x plus 1 over x plus 1. So y is now equal to x minus 1. There is no denominator. My denominator is the value of 1. So when I make 1 equal to 0, that's not a true statement. So I think what's going to happen here is there are going to be no vertical asymptotes. And if you place this into a graphing calculator or a graphing program, you're going to see that it goes on forever. So there are there's no asymptotes that it fails to reach. It just keeps going and getting larger. All right, let's look at the next set of notes. So finding the horizontal asymptote using examining the in behavior. So what I want to do when I'm examining my asymptote, so we're looking at a function and we want to know, where's it going when it moves on forever. And let's see, so our horizontal asymptote is much like our, it'll come to me in a second. But what you want to do is you want to take the power, the greatest power in the denominator, which happens to be the first power, and you're going to divide everything by that variable and that power. So what that means in number 1, I would take negative 2x plus 6 and divide both of those terms by x to the first, and then do the same thing with the denominator. And I have x to the first divided by x to the first minus 5 divided by x to the first. And here is the challenging part. Okay, so when we do this, I know some things are going to cancel out. So x over x is going to become 1, and then this x over x is going to become 1. Now think about it. Now we're looking at these two other expressions. 6 over x. 6 over x. And that, if x is equal to 1, then I have 6. If x is equal to 2, then I have 3. If x is equal to 100, then I have 0.06. So as we see that x is getting larger, my value is getting smaller, right? So eventually the number would look like a 0. So this becomes 0, this becomes 0. So I end up with, looks like a simplified -2 over 1, or therefore my horizontal asymptote is y equals -2. And that's because my function, as it goes off into infinity, it is going towards the value of y equals -2, and that's the end behavior. So looking at this next example, I have x minus 1 over x plus 2 and x plus 2 squared. And my horizontal, actually I don't need to do that, I apologize. So remember my my horizontal asymptote, I take the greatest power in the denominator and divide all of them by that variable in power. So I'm going to divide the first term, x by x squared, minus 1 divided by x squared, all of that over x squared divided by x squared, plus 4x divided by x squared, plus 4 divided by x squared. Now hopefully you remember that if we have a greater value of our variable in the denominator, it's going to be going to 0, so that's going to become 0. This one is going to become 0, and then this expression should simplify down to 1 over 1. And then this would be going towards 0, and then this is going to end up being 1 over x when we simplify the powers. So it turns out that my end behavior is going towards infinity. So this ends up becoming just, x over 1. So that as x increases, the equation increases, so it will go on forever towards infinity. So there is no horizontal asymptote. And then here we go ahead and factor again. I have x plus 2, and then x minus, and I'm going to go with, just looking at it, I am going to try let's see here. So I have x plus 3, so that's going to be x minus 1. And all that over with x minus 2. Since nothing cancels out, that was a waste of my time. And so I can go ahead and get rid of that. Okay, so as we were talking here, y equals, and I can go ahead and, I guess I don't need to factor, but I do know that I have x squared plus 2x minus 3, and then I have x minus 2, and the greatest value of x in the denominator is just 1, so I can just divide everything by x to see what happens. And what's going to happen here, as we just mentioned, is if the variable is greater in the denominator, then it's going to become a 0, and those become a 0, and this simplifies to a 1, and what do we have over here? That simplifies down to a 2, and this expression simplifies to a 1 over x to the first. So as x, y equals x plus 2 over 1, as x becomes infinitely large number, then this whole thing goes towards infinity. So since it's going towards infinity, there is no asymptote. We have no horizontal asymptote. Let's see, so if we go to, so hopefully as we talk about this in behavior, vertical, up and down, horizontal, left and right, we get a little bit better grasp at it. And let's see here. I'm going to go ahead and create the graph real quick. All right, I've gone ahead. I know where it's going to go, so I sort of skewed my graph to the right, to the left. And what I want to do is I'm going to go ahead and factor this. And I have x plus 3 equals x minus 5 times x minus 1. And therefore I know that using the zero product property, x minus 5 is equal to 0, x minus 1 is equal to 0, and then x equals 5, x equals 1. Okay, those, when that denominator is equal to 0, what did we say that becomes? Okay, that's my vertical asymptotes. Vertical asymptotes. And so my vertical asymptotes are going to be x equals 5 and x equals 1. So what I want to do is I can go over to my graph and draw in those little dotted asymptotes. It's going to help me graph later. So, oops, I forgot I need to fix my rating, I guess, or my scale. So let's get rid of that. Let's get rid of that. Get rid of that. Maybe we'll change this scale to just numbers, just regular ones. So some of you are going to complain because I just did that. Okay, so my asymptotes, my vertical asymptotes were x is 5, x is 1, so create these vertical asymptotes. X is 1, 2, 3, 4, 5, x is 5, and x is 1. Okay, so those are my vertical asymptotes that my function's never going to touch. And then it hasn't been, there's nothing, this is plus 0 up here. So then I know my horizontal asymptote, or my end behavior, is going to be y equals 0. And you can look over here at your definition and see that your greater exponent is in the denominator. So my other asymptote is going to be right along here. So if I were to graph this equation, sketch it, it would look something like this. There you go. So you can throw in a couple of values. You could have given a value for x is 3. You could have also given it a value for x is anything this direction or anything this direction, and it would have told you whether it was going to be a positive or negative value to where you knew where to flip it. And I think that looking at those simple characteristics of this rational equation, that's all we need to do for this section. We will come back to 8.4 momentarily, and we'll tackle these two together in an assignment today.